Okay, so this is a question that I've been sent that has to do with organic acids and how to break them apart. And so the acid-base part of this is not particularly difficult, but figuring out the components can be. So I think the easiest way to break this down is to actually draw a formal Lewis structure, because if you haven't had organic chemistry, which I imagine none of you have at this point, you're not familiar with the organic notation. So this is how an organic acid is done in a Lewis structure. And so what you notice here is this is the hydrogen that's going to come off in the acid. So what you can kind of look for in the problems, because sometimes these formulas can get really long. What you're looking for, this is just formic acid, it's the simplest organic acid with only one carbon, is you look for this notation. And my dad always calls it Cu. So you look for Cu. And then, so when you're writing your dissociation, write your acid. And then almost always, this is going to be on the end. This is going to be the terminal end. And so you find your group here. And so when the Lewis structure, you can say you're always going to pull off a hydrogen that's attached to an oxygen. And organic acids are automatically weak acids. You know it's a weak acid because it gives you a Ka value. So go ahead, pluck off that hydrogen, which is this one. And that's going to leave you with your anion. Now, ultimately, it's really not going to matter if the organic notation is just too much. Just use a standard generic acid notation where you just say HA dissociates into H plus and A minus. That works too. The point is you're just trying to set up, you want to break this down into conjugate base and conjugate acid. So let's go ahead and work this problem now that we have dissociated. The first thing we're going to do after we write our equation for K, our expression. So that's going to be your products, HCOO minus, over your reactants. Or if you're using generic notation, this would be H plus A minus over HA. Both of those are acceptable. Okay, now, after that, we make our ice table. And at the beginning, we're only given acid. You have to be careful when you're given a mixture. If you're given a buffer, you can use Henderson-Hasselbalch, but so sometimes you might run into that, and that's not the scenario in this case. Carry down your coefficients in acids, it's easy. And another thing that might help clarify is the acid is only going to lose one proton at a time. So just pull off an H somewhere. And if the problem needs you to deal with conjugate base, it will probably give you the formula. So here we know at equilibrium, we have this. Now let's plug it into our expression. So let's go, I'm gonna do it down here. 1.8 times 10 to the negative 4, make sure you can still see it, equals x squared over 0.2 minus x. Next thing, let's check to see if x is small. I don't have my graphing calculator with me, so hopefully you can still see this one. So we're going to take molarity divided by K. Oh, I didn't put negative 4. Let's try that again. 0.2 divided by 1.8, 10 to the negative 4. Yes, it is greater than 100. So we know M over K is greater than 100. Check mark, X is small. So let's clear the fraction. Times 1.8, 10 to the negative 4. And now let's take the square root of that, which is here on this calculator. Okay, so we got x equals 0.006. Now that we have solved for x, we answer the question. This wants to know the pH. For the pH, we know that pH equals negative log concentration of H+. Do we know the concentration of H+ here in this problem? Yes, we do, because it's the same as X. So just plug that in. 0.06. And you can show me as much of this work or not as you prefer. So let's just take negative, let me find log on this calculator. Log answer. So 2.22 is what I got, because you know I always like to use 2 decimal places on pH. So hopefully that makes a little bit more sense, or gives you a way to break down these organic acids in a way that makes more sense to you. So recap, look for Cu, pull off the H that's bonded to an oxygen, or just use generic acid notation.